I want to talk a little bit about rotations as linear transformations. The text this really is from chapter 2 of the text. The text goes into some of the geometry. I want to go back a little bit before that, actually, to your trig days. So I want to look at, we've got a unit circle. So let's draw in some coordinate axes here. Nice blue axes. I haven't got my tablet yet, so I'm still drawing with the mouse, so everything will be nice and precise. But if we look at an angle on the unit circle, remember it's defined in radians. So say I got some angle, let's call it alpha, hopefully that'll be easy to draw. Then this point on the circle, define the trig functions. Cosine, the x-coordinate was the cosine of the angle. Draw this in here. And the y-coordinate was the sine of the angle. And so hopefully you remember that back from the pre-calc trig days. And so what we want to do now is look at the same circle, so to speak. Or actually not even the circle itself, but the axes and the unit vectors along those axes. So what I want to do now is say, okay, if I've got this vector, right, which is just corresponds to this point over here, right? So now instead of thinking of points in the circle, I'm thinking of a vector that goes from the origin to that point on the circle. So I'm going to rotate this again. Right. So I'm still rotating through the angle alpha, except now the result is just a vector pointing up at this point up here, just like I did over here. And that point on the circle still has coordinates cosine alpha, sine alpha. And it's just now that we're thinking of this as a vector from that point back to the origin. So one question is, of course, that's a transformation. It's a transformation that takes vector 1 to vector 2, where this guy along the x-axis was my vector 1, and this guy now is my vector 2. Okay. So that's a transformation. Why would I think that's a linear transformation then? Well, what does linear mean? It means that if I act upon a vector that can be broken up into a sum, that the resultant is going to be just the sum of those individual pieces. So you should be able to convince yourself that if I take a vector and I break it up into two vectors that are added together, and I rotate that to a new vector, right, rotate it through some rotation of degrees alpha, right, that really is just rotating each part. Right, and the same as if I scale this by some value c, and the resultant vector is just going to be the same vector rotated, scaled by the same amount, c. So what we're really saying is that this transformation has the properties that if I act on a pair of vectors that are summed up, and these are really vectors now, x and y, that the resultant is just the sum of those vectors. So that when I if I broke this up, and the result would just be each one rotated. And technically, right, when I did this rotation of this little piece here, I just sort of rotated the whole thing up. I mean, really, I have to move it back to the origin, rotate it, and then move it back out by the amount that it got shifted. But you should be able to see that all works out. And everything just adds up. And likewise, if I just scale the vector, right, multiply it by some constant, that the resultant rotated vector is still just that constant times the little piece, the main unit vector that got rotated. So a rotation is a linear transformation. I've not done anything with matrices at this point. All I've done is say that, okay, if I rotate a vector, right, I get a new vector, and that transformation is a linear operation. So I have a linear transformation. So rotation can be represented as a linear transformation. Now the question is, can I actually represent that linear transformation as a matrix and do the operation of the rotation by just doing a matrix multiplication? And the answer, of course, is yes. You probably have seen this already. Right? That's the point of chapter 2. So that if I look at this circle again, and put my little axes in here if I can draw them in. Ooh, red this time. So that if I take the unit vector along the x-axis, which we generally refer to as E1, or I'm going to refer to it as EX, and rotate it through an angle alpha, then the resultant vector is really just the vector right? So this vector got transformed to the vector cosine alpha sine alpha. Right? So this vector, another way to write that would be, of course, is that t of my unit vector is equal to this guy. So if I do the same thing along the y-axis, and I look at the, let's see if I can find a nice color for the y guy. Purple's showing up quite enough. Right? If I look at that guy, that's the unit vector in the y direction. If I rotate it through a rotation of alpha, and I get it transforms to this vector. What are the coordinates of this point on the circle? Well, it's really, right, the points on the circle are measured from the x-axis. So it's really alpha plus this 90 degrees or pi over 2 radians, whichever way you want to think about it, right, from the x-axis. So it's really the cosine of alpha plus 90 degrees. Can't write very well with the mouse. And the y-coordinate is then the sine of alpha plus 90 degrees. And getting all run together here. But what that is equal to, all right, it's just a phase shift on the cosine and sine. And so you probably remember back from trig that that's just equal to the sine of alpha. So the coordinates of this point are really just sine of alpha minus cosine of alpha. Cosine of alpha didn't write too well there. Right. So in fact, this vector transforms to the vector sine alpha minus cosine alpha. So we see that, and of course this is just our transform on that unit vector. Sorry, my hand's giving out here. So I can really write this transformation as the matrix. I'm going to clear things off here now and just write it. Right? That the rotation through alpha can be written as the matrix of cosine alpha, and we just take those transformations on the unit vectors and write them as column vectors here as our resultant. And so then I have sine minus cosine here. So for example, if I apply this to r of alpha applied to our unit vector in the x direction, and multiply this out, I just get cosine and then sine, so I just get that same, just get this first column here. Right. If I apply it to the unit vector in the y direction, of course I just get the second column. Right. Just do the multiplication out, so this guy is just this column here. So we see now that we have a matrix that represents that linear transformation that I previously called T. And so I can operate the rotation T from as an abstract linear transformation from R2 to R2 by using the concrete, right, operation of matrix multiplication, rotation through alpha, right, gives me that same transformation. So I have a concrete representation of what I had just really done as an abstraction, doing a rotation through some angle alpha. So I was able to hopefully convince you that that rotation was a linear transformation, and then from that derive a matrix that represented that linear transformation. And that will sort of be a theme throughout a lot of our work in this course. We will have a linear transformation. First of all, we know that a matrix multiplication is a linear transformation that transforms a vector from, into a new vector. But the converse will also be true, that we'll be looking at abstract linear transformations and we'll want to try to derive a specific matrix representation for that transformation. So hopefully you'll see that theme come up again in Chapter 3 and more specifically in Chapter 4.